I am definitely not a stellar variability expert by any means. We've heard from a lot of stellar variability experts already, and we'll be hearing from some more. So I apologize in advance if I don't cover your specific work in this. I'm only really scratching the surface. This is one of the biggest areas of active research in the radial velocity community right now, so there's a lot going on. So let me start by framing the problem. EPRV spectrographs are now reaching incredible precisions. We're able to measure centimeter per second precision of velocities on stars up to hundreds of parsecs away, in fact, even 1,000 parsecs away in some cases at this point. Centimeter per second speeds are about the same speed as what a tortoise crawls across the desert at. So if you think about measuring that speed on a star that far away, it's pretty incredible. We're also down to measuring, the shifts that we're measuring in the spectral lines are actually sort of on the same order of magnitude as the spacing of silicon atoms in the crystalline structure in the CCD itself. So it's a difficult challenge, but we've come a long way, and we're doing really well. So you've seen this plot a few times already. This is the RV semi-amplitude of the exoplanets as a function of their discovery date. Of course, you see that the precision followed a nice power law up until about 2014, when it tended to flatten out. Now, if you consider the precision of the spectrographs, that continued nicely along that power law. So something is causing that floor, and that, of course, is stellar variability. The problem is that we're trying to measure those turtle crawling speeds on stars that look like this. It's definitely not a nice solid body where we can precisely measure that. It's a rolling, boiling mess of gas. I'm going to talk about three main classes of stellar activity that are probably the biggest problems in radial velocities. There are definitely further details into all of these and other sources as well, like flares that we heard about. But I'm going to go through these in this talk. So first of all, this rolling, boiling mess that we see is, of course, granulation. We've seen this plot, and we've seen several talks on this already. What we're seeing here are the tops of these convective cells. As slightly hotter gas rises up to the top, we see those as those bright regions. I like to think of this sort of as the tops of cumulus clouds. You see these big thunderstorms building up. It's kind of a similar process. We're just looking at the very tops of this. These brighter regions are where that gas is rising. We're seeing the tops of those, and then you have the intergranule lanes, these dark lines between those granules, where the gas is sinking back down after it's cooled. The granules are moving up towards the surface with speeds with order of magnitude kilometers per second. And the intergranule lanes are sinking even faster. On average, we see more of the brighter regions when we take spectra of these stars. And what that means is that we see a net convective blue shift. It looks like the surface of the star is sort of moving towards us a little bit of order a kilometer per second or so. These things are not stationary, though, as you saw. They change on hours time scales. So it's something that you have to watch for when you're collecting radial velocities on those time scales. Most of the time, we don't have the time resolution to detect the granulation in radial velocity signatures, at least for the legacy data sets that I tend to work with. So it looks more or less like white noise typically in our data sets. Rotation is a big one. So this manifests due to star spots and faculae as they rotate across the surface of the star. That tends to block or decrease the convective blue shift in regions of the star. And of course, part of the limb of the star is coming towards you, part of it's going away. So as you change that, the mean velocity of the lines appear to change. I'll go in a little bit more detail on that later. There's a huge variability in the amplitude that spots can cause in your radial velocity time series. For the most part, for solar-like stars, it's a few meters per second, but for young stars, it can be much, much greater. M stars as well can be significantly problematic. And then we have magnetic activity cycles. We heard a lot about this morning. This, of course, we see as the 11-year solar cycle in the sun. Up here on the top, top left, I'm plotting the mean number of star spots on the sun as observed going as far back as the year 1700. And we can see the mean number of spots changes drastically between the peak of the peak of the magnetic activity cycle and the troughs. Each magnetic activity cycle is not equal. Sometimes we see 3 or 4 times as many maximum spots as peaks of other cycles. They also tend to last different amounts of time, a little bit, and they can grow at different paces and tail off at different rates as well. The way this manifests in RVs is that as you get more spots filling the surface of the star, that tends to block more of that convective blue shift. And so you're suppressing that, and it looks more like a red shift as you get more spots on the surface. Of course, during these times when the activity is maximum, you tend to have more rotational modulation as well, since you have more spots. This is one thing that's tracked really nicely by the calcium H&K, or S index, as we've heard it called a few times. This is a measurement of the calcium emission in the core of a line. And as you can see over here on the right, where I'm plotting the radial velocity time series for one of my favorite stars, HD 7924. On the top is just the raw radial velocity time series. This doesn't have any of the small planets removed, but you can still see the magnetic activity cycle there as traced by the S index here. You can see it follows that pretty nicely. You'll also notice that at the time when the activity is maximum, you see more scatter in the radial velocities due to that rotational modulation. And it's actually quite well correlated linearly with the radial velocities, which in the past have been used to sort of try to correct this using that linear correlation. So this is a problem, especially for long period planets on decade time scales. And so I wanted to go through one of an interesting story of HD 154345. This is probably Jason Wright's nemesis star. So he initially published this as a candidate in 2007. It was in a paper with a couple other planet detections. And he had this orbit so far. It wasn't quite complete, so he wasn't willing to call it a planet quite yet, but he published it as a candidate at that time. Then in 2009, he decided that there was enough data to publish it as a planet. He had a complete orbit, and it was interesting because it was one of the first sort of Jupiter twins that we had discovered. It's a very similar mass and orbital period to Jupiter in our solar system. So it was an exciting discovery at the time. Now this plot is straight out of that paper where he showed the S index plot right next to it here, which does suspiciously trace that same signal that was detected in the radial velocities. This is really pretty early days, and we didn't fully understand what that meant. And you'll actually notice there's 2 different stars plotted on that S index plot. One is Sigma Draconis 185144. It follows a very similar trend in time as the S values for this star. So he sort of blew that off as a coincidence. So first of all, we saw it in 2 stars in almost the same phase in time. So there may have been some sort of instrumental issue with measuring this. And Sigma Draconis shows a very stable radial velocity time series over the same period of time, about 1.5 meter per second scatter, not this huge 10 meter per second variation. So he basically said, well, this is probably not caused by the S index or the activity because it's too large of amplitude. We haven't seen that before, and we don't see it in other stars. Over the next decade, we continue to monitor this star, both with the S index and the velocity time series. Now, I've had to cut off the first part of this, so we're only seeing a second orbit here. But in a conference proceeding in 2015 or 2016, he mentioned, he made this statement here, saying that continued monitoring of this star since 2008 has shown that the activity cycle continues to be well correlated with the RVs, amplifying that coincidence. Similar correlations among a small number of stars had been discovered, so we started to see S values that, magnetic activity cycles that showed similar amplitudes. And so he said this cast doubt on the planetary hypothesis and basically was convinced that this is actually just a magnetic activity cycle and no longer a planet. Then we continued to follow this for another decade, and shortly after that announcement that Jason made, we noticed that the S value time series is now 180 degrees out of phase. You see the peak is right here, but the minimum in the RV is here. And so we thought that that might be a planet again. And by the time we published the California Legacy Survey, we were actually fully able to separate the two periods of the signal from the planet, and it was back to being a planet again. We see this quasi-periodic activity signal with a period of 7.6 years, and a planet on a circular orbit with a period of 9.3 years. So it went from being maybe a planet to not a planet anymore to a planet again, all in the span of a couple decades. So one way we've learned to compensate for stellar activity over recent years is Gaussian processes. Up here on the right, I'm showing a plot from a review paper that Dan Foreman-Mackey wrote, where you're seeing the number of times Gaussian process was mentioned in papers listed on ADS as a function of time. You can see in about 2010 to 2012, that really exploded. That's on a log axis on the y-axis there. So Gaussian process were really the hot thing starting in about 2010. These are especially useful for rotational modulation. It can be useful for other signals as well. But it's important that we know both the planet's orbital period and the rotation period of the star, if that's what you're trying to correct for, or the magnetic activity cycle. And they're also useful because we can constrain them using a lot of different sources of data all at the same time. So you can simultaneously fit the rate of velocities, the calcium H and K index, the photometry, CCF characteristics, et cetera. All things that shouldn't be affected, or things that only trace activity along with the rate of velocities. One issue for rate of velocities is that sometimes it's difficult to disentangle quasi-periodic signals from fully periodic signals. And the fact that they are quasi-periodic tends to make them blur out or leak into other periods in Fourier space, which is typically how we do exoplanet detections with RVs. So over here on the bottom right, I ran a quick simulation just for the purpose of this talk to demonstrate a known issue with Gaussian processes. So I just simulated a RV data set, injected a planet with an amplitude of 6 meters per second, easy to detect, and did a simple fit with no Gaussian process, and that's the posterior distribution I get out in orange there. Pretty good. Then I injected a stellar activity-like signal using a Gaussian process, and then fit the RV curve with the same Gaussian process. Well, not starting at the same place, but a Gaussian process. And you can see that the posterior distribution is now biased low slightly from the input truth value. Now, this is because Gaussian processes are highly flexible and they can eat up a lot of signal in Fourier space, but this is also a bit of a contrived example. The GP that I injected was very close to double the period of the planet that I was trying to recover here. And so that, of course, can make it eat up the signal even more since it's at a harmonic. What's even worse, though, is in reality, if you had seen this star in rate of velocities, you see a quasi-periodic signal at double the planet, and then you see another signal at the harmonic, we probably wouldn't determine that was a planet at all. So in reality, you get zero mass and no planet detection at all, which obviously screws up your exoplanet demographic studies. So what are we really trying to do in radial velocities? Well, we're taking this beautiful, high-resolution, often optical spectrum with thousands or tens of thousands of spectral lines, millions of pixels of flux measurements, and we're taking all of that information and turning it into one measurement with uncertainties. And it strikes me as we're really typically throwing away a lot of the information by trying to do that. One thing that we know about the way that activity affects the rate of velocity is separate from planets is planets are creating a Doppler shift. That means that all of the lines are shifting in unison together. Typically, a lot of the sources of activity, not all, but most, create some sort of line distortion which moves the center of mass of the lines as measured when you fit your Gaussian to it or whatever, but the lines don't actually move. And they often don't move in unison, as I've simply plotted here. So the distortions come from the fact that when we measure or we observe an absorption line, we turn that into a cross-correlation function. What we're actually measuring is a composite of a bunch of absorption lines that are emitted from different places on the disk of the star. Some of them are moving towards us as that star rotates, so they're slightly blue shifted. Ones in the middle, of course, are nice and sharp, and then ones on this side are red shifted. Of course, those are all blurred together, and we see that typically as a broadening of the spectrum, which we can use to measure the rotation of the star in V sin I. As spots go across the surface of the star as they rotate in and out of sight, like I said, that tends to block some of the convective blue shift in that region. It also blocks some of the flux in that region. So instead, we're essentially cutting out some of this portion when the spot's over here, then we're cutting out some of the center portion. And this is illustrated by this plot here. It's actually demonstrating an RM effect of a planet shadow crossing the surface of the star. But spots create a similar distortion to the spectral lines. So over recent years, there's been some exciting developments in stellar activity mitigation. There's a lot of different axes that people are researching here. But one thing that people are trying to do is start to measure the rate of velocity of individual lines or small sections of lines that are close to each other to determine which lines are more or less sensitive to activity. So here on the right, I'm plotting showing a plot from Xavier Demuth's paper in 2018, where on the y-axis here, I'm showing the RV uncertainty of each point is a small collection of spectral lines. And on the y-axis, I'm showing the scatter of those lines, essentially, in the time series. And on the x-axis is the correlation coefficient between the radial velocity of that line and the radial velocity of the full spectrum of all the lines combined. So you see that ones that have the lowest correlation coefficient with the overall velocity also show the higher scatter. Now you can use this to select the very best lines here that you show in red. And if you do that, you can improve the radial velocities quite a bit. So on top is the same data set, the raw RVs, before you make any selection of lines. In the middle, the colors have been reversed for some reason, but the red is when you only select the lines that are most sensitive to activity. And then the blue are the small collection of lines that are least sensitive to activity that show the least scatter. So you can improve the precision and the overall RMS of the radial velocity curve quite a bit. There's a couple problems with this technique. One is that we're not really sure that all stars act the same, so you might have to do this for every star, or figure out which lines are appropriate for each star individually. And you're going to need very high signal and noise. You can see we're down to only 26% of the radial velocity information in that full spectrum that we're using to derive this final curve here. So again, you're throwing out a lot of the spectrum. You're going to need very high signal and noise, both to measure precise velocities on individual lines and to get enough signal and noise in your final curve with only a small fraction of the lines. Now, this technique actually reminds me of the old iodine technique that we've been using since the late 80s, actually. And in the iodine technique to detect radial velocities, of course, we take a cell of gaseous iodine, we pass the stellar light through that imprints an absorption spectrum on top of our spectrum, our stellar spectrum, and we use that as a wavelength reference. We then fit in a bunch of small chunks, the spectrum plus the iodine spectrum, And then, in order to get velocities that are probably better than high-res should ever be getting, we look at the velocities of each one of these chunks. We look across time, and we essentially use that to determine chunks in the spectrum that have higher scatter than others. We select chunks that are showing the best performance, and that's how we get the final RVs from instruments like high-res that use this technique. So we're sort of coming full circle and going back to the technique that we started with here, and understanding that individual lines act differently, and it's important to split up the spectrum into a lot of smaller chunks. This is another exciting prospect that recently was published by Jared Siegel. So we know that the lines, different lines from different elements are formed at different depths in the atmosphere. And we can also look at the change in not only line shapes, but line depths, especially if you break those up by lines that you know are formed near the surface or near the photosphere of the star. And if you track the depth of lines that you think are activity sensitive, you can see that it traces the activity here very nicely, very close to the S-index and very close to other CCF parameters as well. So it's another way to measure the activity. And if you were to fit that as another activity matrix, or in your big Gaussian process matrix fit where you're fitting all these parameters simultaneously, you can do even better. You can also use that to interpret what's happening on the surface of the star using the FF prime method, which uses the derivative of the changes in line depth as well as the actual change in line depth. But the result is quite impressive. So here you have this rate of velocity time series of alpha sen b. You see a scatter of 2.6 meters per second. We've shown a bunch of different techniques here. One is that line selection technique that I just went over. When you select just the best lines for this star, you decrease the RMS by quite a bit. You do quite well. But if you do a GP fit to all of these activity metrics, activity indices, you can get a much better result, a very flat RV curve at about 1 meter per second precision. So one thing that some people might know about me, I've been working a side gig as an AI engineer as well, working on natural language processing. And over the past few years, I've really seen an incredible transformation in the capabilities of AI. You've all probably seen it as well. You've started to use ChatGPT in a lot of your work, I'm sure. If you haven't, you should, because it really helps your coding. And this is all thanks to a revolution in the computer science where we're using these things called transformers now. Transformers are basically a complex way to use neural networks and layer them on top of each other. But what's important about them is that they can discover relationships in the data without any training. They can discover relationships in the data that are separated far apart from each other and far apart in time as well. And you don't need to have a large data set with precisely labeled data in order to train these models. Now, a problem with this is that these foundational models that power ChatGPT, et cetera, are trained on the entire corpus of text on the internet. A much bigger data set than we have access to in astronomy typically. And they also are very computationally expensive. They have billions of dollars worth of GPUs that they train these models on for months or years at a time. And of course, astronomy data sets and budgets just aren't capable of doing this. But these foundational models already exist. Although they're trained for text, typically, there's also ones trained for images. There's also models trained to determine how proteins fold, given a sequence of amino acids, or what mutations in DNA might cause certain problems. So we may be able to use these foundational models, train them to be specialized in the tasks that we need in astronomy, and take advantage of all the work that's already been done here. I think this is really where a lot of computing is going. So I think it's important that we stay up to date on this. We try it out in various applications, see how well it works, and see if it's going to work for our problems. So in summary, we're really good at building spectrographs now. That's not our limit. Stellar photospheres are moving targets, and they're always going to be difficult to make these very precise measurements. Stars are always trying to trick us, whether or not you like it or not. And radial velocity data sets are actually starting to get large enough that we might be able to train these complex AI models. The last thing I'll mention is, we have about, each one of these spectra has millions of data points of flux measurements. And with high res, we have about 100,000 spectra. We have similar on APF. KPF, NUID, we've collected that already thanks to the solar data. So we actually are starting to get a huge amount of data in radial velocities that we could use to train complex AI models. And thanks. I'll take any questions.
Thank you. Any questions? See one here.
Andreas Quirnbach, Heidelberg University. Thanks for the nice talk. I'm wondering about the methods like line by line and similar methods. They have typically been tried on relatively short sequences of data, whereas you showed at the beginning, of course, solar cycles. So the statistical properties of the Gaussian process should change over time. So do you think it is good in the end if you have something, say if you have a 10-year time series of RV data that the planet signal is constant, whereas the statistical properties of the stellar activity signal changes over time, or will this kind of confuse algorithms also? Machine learning techniques, will this be good or bad?
I think we could definitely take advantage of that. It's similar to the way that we could take advantage of the fact that all the lines move in exactly the same way, where activity doesn't typically cause that. I think we can use that to separate out stable signals from these quasi-periodic changing signals. But as I mentioned, the quasi-periodic nature of those signals and the fact that they are changing makes them leak in Fourier space. So anything that's nearby to that period is going to be confused, at least partially, with the activity signals. So I'm not sure how we get around that, but I think we have to go back to the spectrum.
Time for another one or two questions.
So I noticed you didn't mention the oscillations, the P modes, because these days people just integrate for the typical period. But firstly, stars aren't narrowband; they have oscillations over a wage of periods. So such averaging will never be perfect. But also the amplitude of the oscillations varies with the depth of the spectral line and with which line you use. So are people starting to look into that as a possible way of mitigating that particular contribution?
I'm sure people are looking into that. I have not personally looked into that, but this, like I said, this field is rapidly growing. It's one of the highest priorities in the field of radial velocities to study how we're going to mitigate stellar activity. And I think honestly the best way is to sample over those P modes so that you can actually resolve them and see them and subtract them rather than averaging over them, because then it just looks like some sort of white noise in your data.
I agree completely.
Yeah.
Time for one more question if the next speaker wants to come up during that. Thanks.
Yeah, you have a magical wand to get us the volume of data that we need to train the transformers. What order of magnitude would you want, and what could we produce with that improvement in the training and the data?
Well, typically these models, these transform models have trillions of free parameters. So we need a lot more data than that, 100 trillion or so. And I think in radial velocity data sets, we're getting close to about 10 trillion pixels. It's not fair to count each one of those pixels as fully independent necessarily either. So we probably still need an order of magnitude more data to fully train our own foundational model. And then, of course, there's the issue of cost. You're going to need a lot of GPUs and a lot of electricity to power all that for months to years to train a foundational model from scratch. But it's really amazing what you can do with these models that are trained in totally different things, unrelated. You can really fine-tune them to specialize pretty well in a wide variety of tasks. So I think right now, that's probably the most promising avenue that we can go on.
Give our speaker one last round of applause.
Thank
Thank you, Jay.